right, good morning. So I did not quite finish grading your exams, so I'll have those for you on Tuesday next week. I did start, and I think at least on the first problem, most of you did pretty well. A couple issues here and there, but didn't seem to be too bad. And then from there, I think it was looking okay. Didn't get through everything. But we'll have those back to you, and we'll go through those problems essentially on Tuesday next week, in case you have any questions or issues with that. Today we will resume talking about chlorination, disinfection in general. Essentially, where we left off, we had taken a look at a little chlorination problem with chlorine speciation, solved that, and found kind of the ratio of hypochlorous acid, so HOCl compared to OCl minus, given some pH. So it was a little bit of a reminder of kind of that equilibrium chemistry. We'll talk a little bit more about that, I think, and have another example problem for kind of kinetic analysis of some data. But picking up with the concept of chlorination, one of the things we are concerned about is reaction with other stuff. So chlorine is going to react, since it's highly reactive, it's going to react with all sorts of things. And if we start adding chlorine groups to random molecules, then we could actually make some things more toxic. In fact, if we're using, let's say, bromine or iodine as a disinfectant, which occasionally we do in swimming pools, sometimes we use bromine instead of chlorine for, again, sort of a occasional use, like hiking or something. You might have iodine tablets to disinfect water. Effective, but probably doesn't taste so great, and you probably wouldn't want to be drinking that all the time. However, if you have these things and they react with stuff in the water, and mostly I'm talking about natural organic matter or some other dissolved organic matter, because this could apply to wastewater treatment as well, and we wouldn't really call that natural. But if it reacts with some organic matter, then we're potentially halogenating, so adding these halides to the organics. And if we do a lot of that, then we get things like trihalomethanes and haloacetic acids and other groups where we have some organic molecule that has now been halogenated and is now a concern for toxicity and for carcinogenicity. Didn't quite say that right, but you get the picture. The thing is, there's like thousands of different types of molecules if we consider just natural organic matter. If you consider making tea, you've got lots of tannins and tannic acid and stuff, but there's all sorts of flavors and just different things based on those leaves that are dissolving, right? The natural living organisms have stuff in them, and those molecules are breaking apart. Whatever cells were creating them, wherever they came from, there's just a wide variety of stuff there. So when we react these then with halides, we just kind of don't know precisely what's going to happen. And so then we use these particular metrics where we can quantify kind of the bulk amount of trihalomethanes or haloacetic acid. So a trihalomethane then would look something like this. We have R as our symbol for the rest of the organic molecule, right? It's kind of how in organic chemistry you'd see it, bonded with some carbon at the end. And normally you'd have 3 hydrogens here. Each of those would be hydrogens. But this time we're going to substitute and then replace those hydrogens with chlorines. All right. Okay, so that means that would then be a trihalomethane group on a larger molecule. You could also have this R be just an H, and then it is literally trihalomethane. It's probably another word for that. That's chloroform, is it? There's that is a specific molecule, and we know it by a different name, because dichloromethane, that's chloroform. Anyway, so we would recognize that if it was just just a hydrogen there and has particular properties. But we also classify any group on one of these big organic molecules. This might be one of these natural organic molecules. It's got all sorts of different little functional groups on it, all sorts of end chains and random stuff. To halogenate that, then we could have different parts of it, and maybe it breaks apart further, becoming these trihalomethanes. Okay, so that's a concern. That means that when we're chlorinating our water, we want to be careful to try not to have too much organic matter there. It's kind of inevitable. It's sort of hard to remove, but we might select a groundwater instead of a surface water, or we might run some carbon filtration first to reduce the organic matter load. And we also might aim to do less chlorination. So the extent to which you're going to have these formed will depend on the concentration of chlorine you're using in that contact time. We'll talk about soon. So maybe you use some ozonation and then chlorination, or maybe UV light and then chlorination. You might set up your system to avoid having too much straight chlorine as your disinfectant. Okay, so another concern here would be our chlorine is basically demanded by different substances in water. So just like it can react with organic matter, it can also react with, let's say, metals that can be oxidized. So if we have some iron in solution, the chlorine could react with the iron to oxidize it further, maybe take it from 0 valent into 2+ to ferrous, or maybe all the way to ferric. And even if it's not going to be a iron chloride molecule resulting, it could do the oxidation, and that would take away, or essentially that would give the OCl an electron, and so then it would break and become a Cl- just in solution, and the oxygen would probably be given to the iron and make some sort of a ferrous or a hydroxy iron of some sort, something like that. So anyway, there's all sorts of different things that could happen here. So let me just write this out. So let's say we have an HOCl plus Fe. Could go, and I'm not going to be exact about all this, but it could be something like, so I'll just give this little squiggly because this is an approximation, right? To some sort of FeOH and Cl-. So something along those lines could happen. And the fact that the chlorine is now a chloride, this is pretty unreactive, right? This is like the table salt stuff, the chloride side of that. So chloride is not our reactive species. It's the OCl or HOCl. It's really that has that strong oxidizing potential, because the chloride here has that extra electron, so it's kind of happy. It's already oxidized something, already stolen that electron from someone else. And now this form of iron or whatever is the appropriate, maybe it's FeOH2 or something, whatever the proper chemical formula is and reaction, something along those lines will happen, and we'll have oxidized from the 0 valent for the iron to the +2 here. Okay, so that's going to demand some chlorine. So we're going to get less usable chlorine. When we thought we dosed it to be 10 milligrams per liter, now it's reacting with all this iron and other metals and reducing the total amount. We would also consider the fact that, hey, this is reacting with 0 valent metals. What happens to our pipes, right? So just kind of a side note here, pipes, or pipe corrosion is a concern for overchlorination, right? Now, there's a few things we do for that. Namely, we add some corrosion control, make it less likely for the pipes themselves to be vulnerable to it. And we also typically operate our distribution systems in a manner that we expect to have mineralization, so mineral deposits slowly over time, which will eventually choke the pipes and constrict them and prevent them from working. But we'd rather that than having them deteriorate, leaching away the metals, eventually exposing it to open groundwater, contaminated sources, and potentially leaching lead particles off of really old pipes. So we protect against all of that by causing the water to be slightly on the scale of forming the mineral scaling deposits rather than corroding. So that's the oxidizing sort of oxidation reduction sort of stuff. Okay, so oxidizable metals demand some chlorine. Then we have nitrogen groups that are going to demand chlorine in a way that, let's say we have an NH3 and HOCl. It's going to look something like this. This will become NH2Cl. So that would be a monochloramine. Could go further and be NHCl2. Actually, is this right? I think that's right. I think I've got something slightly wrong here. I feel like I've got something slightly wrong. Anyway, we can have mono, di, or trichloramines. So I'm going to come back later, but it'll be something like this form, right? 1 nitrogen to 3 chlorines. Approximately. So we get these monochloramines, dichloramines, trichloramines. Those are going to form if there's anything containing nitrogen around. So even with nitrates, we could be forming them. And so the deal is that's also demanding some chlorine. And as we see, even these chloramines can, in a way, demand more chlorine. And so having nitrogen in our system is going to be a source of chlorine demand that we have to overcome before we are getting a steady response to, okay, we add a little bit of chlorine, we get that same amount of free chlorine ready and available. Because really a lot of what we're talking about here with this, what we call breakpoint chlorination, is we want to know at what point can we add a milligram per liter and we get a milligram per liter. Okay, and so what this looks like in practice would be this. So this is a graph I found online. Essentially, when we're looking at chlorine residuals, meaning how much free chlorine or potentially this combined chlorine we call essentially monochloramine, or chloramines in general, are combined, means chlorine is combined with nitrogen. So combined, I'll just write that up. So combined chlorine is usually considered monochloramine or whatever remaining chloramines exist. And we actually want to use that to an extent for our distribution systems because it is a slow-acting chlorine. It does not kill microbes fast. It kills them quite slowly because it's just not very reactive. But that also means it lasts longer in our pipes, and it doesn't destroy our pipes so badly. Right? So actually, it's a pretty nice thing to use, and we actually would add enough ammonia to achieve a desired amount of monochloramine, even if we had none in it to begin with, none in the system to begin with. Okay, so let's take a look at this. We have, when we first start adding, so this is the chlorine dose here, we're adding chlorine, and the first, let's say, milligram per liter of chlorine, or ppm, that we add, we essentially get no impact. Now, this is just some example water, right? This is maybe a typical surface water. So almost no impact because we're oxidizing these metals. That's kind of the first thing to react, and we're just not getting much of anything. Then the next 4 or 5 milligrams per liter we're forming these chloramines. So it's definitely not one-to-one growth, although it starts growing decently, up to the point where we have nearly 3 milligrams per liter of actual chlorine in the system. We're forming these chloramines, and at this point we have gone to the point where we have mono, di, and tri. And then the excess chlorine ends up, the more we add, we ultimately get less and less, because what happens is we start reacting with especially the di and trichloramines to oxidize them further. So we'll be left with some monochloramines down here at the end, primarily. There's going to be a mixture. And monochloramine is not super smelly, but it's a little bit smelly. The dichloramine and trichloramines are the particularly irritating and smelly ones, and that's what if you feel like a pool has been overchlorinated, it's actually you're sensing the chloramines. It's mostly the di and trichloramines. So the stinky smell, like the stinky chlorine smell, the burning in your eyes if you open your eyes underwater, that's really di and trichloramines, and that means there's been a fair amount of nitrogen-containing groups added to the water, and a charitable person might say, oh, there's been a lot of people sweating in the water. Not so charitable interpretation is, been people urinating in the water. This is a lot of ammonia groups coming out in urea and stuff. So will make you think twice next time you're like, oh, that pool is so chlorinated. At least it's chlorinated, right? Well, yes, it probably has a lot of chlorine, but a lot of di and trichloramines as well. Okay, so what's happening here is essentially we're taking those and reacting them further, driving off to some chlorides as a byproduct, and probably some nitrate, which is more oxidized than the amine side of things. Okay, so with that, we end up getting this weird effect where we're adding more, but it's reducing. Okay, but we're getting it back more towards just simply free chlorine and monochloramine. So at some point, we hit that break point, and after that, we're off to the races. Any amount we add is the amount we're getting back. Okay, so this is what we would call breakpoint chlorination. It's an important concept for applying chlorine to understand, we're not going to get necessarily exactly 5 milligrams per liter back if we add 5 milligrams per liter. But once we're past this mark, which we could test experimentally, then we're good. And, as pictured here, maybe that's 7 milligrams per liter after that point, and we essentially have 1 useful milligram per liter of combined chlorine. Then we add to get our free chlorine residual. So if we're doing a disinfection step, then what we would want to do in a contact chamber is have some knowledge about how much it's going to take to get to the break point, and then say we want 5 milligrams per liter of free chlorine in our system to contact with our water for some amount of time. Then we would say, that first milligram per liter is all combined chlorine. That's just going to stay there essentially. So we need 5 on top of that. So we need to get to the 6 mark up here, so that we have a net of 5 milligrams per liter of free chlorine. That means we have to go to here, the 7 mark, add 5, get to the 12, and that's going to give us, or if I did that right, that'll give us our desired result, right? However, whatever way the math works out there. So our dosing is going to be related then to not only the pH like we talked about last time, but also the amount of other stuff in here. Um, yeah, and now this can also sort of show you why, as we think about the presence of natural organic matter and how reactive that, or the potential to form disinfection byproducts, if our water, if we did not have any control of the nitrogen, there's a whole lot of nitrogen there, then our dosing is going to be quite large here. So there's going to be more and more potential to disinfection byproducts if we're dealing with a whole lot of chlorine in the first place. So maybe if there was a step to be put in to reduce the chlorine before we even got to that could help reduce the chlorine requirement. Okay, so that brings us to quantification. How do we then kind of quantify that? I've mentioned this already, but the amount of chlorine we need. This is the CT concept, or contact time. We call it CT, and you could think of it as short for contact time, but it's maybe even better to think of it as short for concentration times time. So this is essentially the amount of time your disinfectant has to contact and therefore interact with, react with your pathogens. So if you've ever done some cleaning with bleach, you know that you want to spray it on, get it, let's say on your countertop, and let it sit there a few minutes. It's probably a good idea to give it that time to eat away at whatever's happening, right? You probably can recognize a similar concept. I mean, even cooking, you get to some temperature and you hold it for some amount of time to get your desired result, right? It's essentially letting the reaction play out. Whereas if you, let's say, got some bleach or something, I mean, maybe you're bleaching your hair on purpose, or maybe you're trying to not bleach your hair, but you got the bleach on your hair, right? So you would know that you either need to get it off real quick if you didn't want it to be there, or you need to let it sit there for some amount of time for the bleach to act. So essentially, that's this concept, right? You have a dosage, and we're talking about chlorine dosing in terms of the concentration we're using multiplied by the time we give it in contact with the pathogens. So that'll give us a sort of a revised rate constant for our reactions, because it's going to depend on how much of the chlorine or chemical disinfectant we have there, and it's going to depend on the amount of bacteria or whatever pathogen we're dealing with that's there. And this is called, we know this as Chick-Watson kinetics. So this is, I guess, the researchers that first kind of established this. And essentially, it's going to be a first order decay, so really focusing in on how the number of bacteria or viruses or whatever is changing over time, dN dt. And instead of just having a simple K times N, we have this K times C times N. Now, this is giving us a rate constant specific to the reaction between this chlorine or whatever disinfectant we've chosen with that particular organism. And then the C is going to be the concentration of our disinfectant. We have it raised to the power of N. That is a coefficient that's giving us a way to deal with non-ideal reactors. So if we have poor mixing or a poorly diluted system where maybe I put a drop of chlorine in here, but I'm keeping it very, very still, just sitting on a counter for a long time, that chlorine may not disperse into the entire bottle, at least not right away. And so if we have a poorly mixed or poorly diluted situation, this N could be less than 1, in which case our chlorine would not have its full effect. Right, so usually we would assume this is 1, because usually we're dealing with ideal reactors. But I wanted to point that out. That's part of the Chick-Watson kinetics, and that gives us a way to deal with scenarios where not all of the stuff is happening right there, or not all of the chlorine is acting like we want it to. Okay, so N is the number concentration of some pathogens, number per liter. C then would be the concentration of the disinfectant, something like milligrams per liter, maybe millimoles per liter. Talked about N. K we will call coefficient of specific lethality. And so let's take a look at the units here. We have dN dt. This is going to be a number concentration per time. So that would be a number per volume per time as the units, right? So then this KCN has to have the same units. We already said that the C is, let's say, milligrams per liter. For the C, I'm just going to write it like that. The K, we'll check what units that needs to be. And then the N is number of pathogens per liter. Okay, milligrams, I said milligrams per liter. Okay, so then we have milligrams per liter, pathogens per liter multiplied here. So, and what we want ultimately is number per volume per time. So for K then, first of all, we know it has to be per time to get a time at the bottom for that. So this should equal negative KCN, whatever units there are. So I'm doing the units for KCN right here. So we have something over time. We need to get rid of one of the liters so that that can cancel with one of these. That way we're left with just one volume term on the bottom. We've got a number term on the top, and we've got this milligrams we have to cancel as well. So we say milligrams on the bottom here, milligrams per time. So liters per milligram per time should be K milligrams per liter if C is in milligrams per liter and N is number per liter. So that's how the units are going to work out. And if you think about it, this K in particular starts looking a lot like our zero order kinetics. But it's not. It's going to be first order kinetics because when we combine it with C, if you look at this, you multiply K and C together, and we're going to call this K star, K times C. We'll say that's just some mashed together constant. K star is in per time, right? So the deal here is it's almost as if we just have a K, but we have another equation for K, and that equation for K is this other K times the concentration we're using. Okay, so it's actually simpler, much simpler in a way than our flocculation stuff. We just have a definition for K. We know it's going to be first order because it depends on how many bacteria are there. That's going to be relevant. We're removing some portion of them over time. So disinfection then is this whole thing with the units. It's important, and this gives us a way for the chlorine concentration to matter and the amount of time we put in it to matter. But ultimately it comes back to, we can write this with a K star as a very simple reaction that we've dealt with many times already. Okay, so then we could put this reaction into a plug flow, which is most common, or a batch reactor if we wanted to. Make sense? So the K star is the combined. In this scenario, this example, if I'm using milligrams in minutes, that would be per minutes for K star, as if we put minutes here. Okay, so that's the essence of Chick-Watson kinetics. Now, one thing you might notice is technically the concentration could change over time. Chlorine is reactive. Maybe it's reacting over time. We're reducing the amount of chlorine we have. That means this entire reaction is no longer going to be first order because it's depending on two different things changing. It gets complicated. Fortunately, we can usually assume we can achieve a system where our chlorine is essentially constant for some amount of time. Or we can at least say we have at least this amount of chlorine the whole time. So that might be the better way to set up the system so we have at least 5 milligrams per liter of free chlorine at all times. That means that maybe we had a little better, but here we are. Okay, so one of the other aspects here was the pathogen specificity. So if we flip back for a moment, we had as our regular K here, we called it coefficient of specific lethality. And I want to elaborate on that. So the coefficient of specific lethality is referring to a specific pairing of a disinfectant with a microbe. Okay, so I have a plot here that is looking at what's called MS2 bacteriophage. Disinfected by essentially what's called singlet oxygen. This is a research topic from my actually from my graduate school that I'm kind of revisiting now, but essentially we're producing different amounts of singlet oxygen, and that singlet oxygen is causing the viruses to is destroying the viruses essentially, so killing them over time. And so when we add different amounts of this photosensitizer that produces the single oxygen, which is acting as our disinfectant, we have some known relationship between how quickly they're dying and how much single oxygen we have in the system. So if we produce more single oxygen, we get very rapid decay. And here I'm plotting log of the number over the initial number. So that's a 5 log reduction, so that's 99.999% reduced in a few minutes under these conditions where we added a lot of it. Whereas if we add very little, we get almost no effect, maybe no effect at all, or add a little bit, we're getting some impact, but it kind of reached a point where we weren't getting much more over time. So that there's some complications there. Normally we would kind of expect it to be more linear on a plot like this. There's some reasons for that, not going to go into, but essentially what I'm showing here is like this is one specific pairing. We could look at the same type of plot against E. coli, let's say, an organism that's a little more protected. It's not going to be as vulnerable to the single oxygen as these viruses. And so we would have a different K, a different coefficient of specific lethality for that scenario. And in fact, in that work, we did have a different, a noticeably different reaction. So that K then becomes pretty important to learn things, either to design a system or if you're studying how effective your disinfectant is. You're often looking at that K, which you can find by looking at that plot, especially if you go ahead and take the natural log of n over n naught over time, then the slope of your curve here is going to be your K star. And then given that you know how much concentration of a disinfectant you put in, you can find the coefficient of specific lethality, right? Okay, so that's just kind of tying it in a little bit to kind of some research topics here. So let's take a look at an example then, and give you a chance to apply exactly that way of thinking about it. So here we have, this is not our book. I think this is one of the ones that's available online though. So an example problem, it says the data for HOCl disinfection of poliovirus at a concentration of 1.8 milligrams per liter, so concentration of HOCl, is shown below. It's adapted from a study in 1979. Temperature was 20 degrees Celsius. They're giving us that information to give us some indication of the Ka or the pKa. And I'm just going to say, let's use 10 to the minus 7.54. There's probably a lookup table somewhere, or we could look up, I guess it's probably the Arrhenius equation or something, that we could find this equilibrium constant based on the temperature and stuff. I'm not going to go into that depth about it. So let's just use Ka as 10 to the minus 7.54. The pH was 6, and then it says determine the rate constant of inactivation assuming Chick-Watson model applies with an n value of 1.0. Okay, so this is going to require a graphing calculator. So I'll pull up Excel and kind of set it up to show you how I will do it. But go ahead and work on solving this problem. Specifically, consider the fact that not all of the 1.8 milligrams per liter. Let's see. Okay, there's two ways we could think about this, and we'll take the simpler route for the sake of time. We could consider that what they mean here is that exactly 1.8 milligrams per liter is HOCl, or they might, maybe they're saying that the total chlorine is 1.8 and then it's at a pH of 6, and so then we would have to say, well, only a fraction of this is actually HOCl at pH 6. So for now, for the sake of time, let's just say all of it is this is 1.8 milligrams per liter. Okay, so do take a moment to think about what you would have to do if you did have to convert that, though. That's a worthwhile problem, a lot like what we did last time. So we could definitely connect it further with the actual rate here. Okay, so then essentially what I'm asking you to do is find K. I'll give you a few minutes to do that. guys get an answer? Not yet. Just a little reminder there for you. K star is K times C to the N, N was 1. So K is going to be K star over C. The units of that should end up being liters per kilogram per second. I'm going to go ahead and give you a little disinfection quiz just to kind of test our working knowledge here, and have you answer the problem. But don't stress about it too much. I mostly wanted to give you a chance to give the problem a shot, and I'll kind of walk you through it in a minute. Should be everybody. Okay, so what is the most common reactor type used for disinfection? It's the batch, CSTR, plug flow reactor, or second order. Okay, good. Nobody answered the reaction order, so it's not a reactor type. A lot of you answering CSTR. I mentioned it earlier, but a plug flow reactor is going to be the most common because essentially what you don't want, and I think I mentioned this last time as well, what you don't want is water mixing as soon as as soon as you add water into a stirred tank and there's water leaving, some of the water you just added is going to leave, right? So that means that even though you're diluting the number of bacteria, because you're also reducing the number in here, you are still getting some just directly leaving. And we don't want that, right? We want it to make sure we have contact time with the water, so we send it through a plug flow reactor so there's no mixing with the front and the back. That also gives us kinetics that sort of act like a batch reactor. Now, to study a system, batch is the most common. So maybe you thought of me saying that because that makes it simple. That's like what the example we were just looking at. We're just looking at the decrease over time. That's what we do in my lab all the time. So we say, yeah, this little batch reactor, we just watch what happens. So if that's what you were thinking, that's perhaps good there. Okay, so what is a typical reaction order for a disinfection process? So 0, first, second, or third. Okay, good. So basically it's going to depend. We're going to be removing some portion of the bacteria or whatever over time. So we'll have some dependence on the number that are there, rather than just, because a zero order would have to be like, okay, I'm going to grab 50 bacteria out of this liter, like every minute or something. And it would be pretty difficult to have a system that would do actually just that. So it's going to depend on how many are in there. Okay, in the equation, dn dt equals negative kc to the n times n. What does the c stand for? The upper gate. Is it the concentration of pathogens, concentration of disinfectant, dilution factor, or contact time? Okay, so somebody's just like hitting the red button. Okay. So it's the n would be the concentration of the pathogens. And it does get tricky. I'm teasing about and in my bigger class, there's inevitably someone hits the wrong button and is like, oops, Anyway, so it can be tricky there because we often have done dc dt and then dn dt. So here we're looking at the pathogens changing, the n, and the concentration of the disinfectant, C, is a part of that. And we could put a little n to the nth for the reaction order, but n would be 1, right? Because it's that's that portion. All right, somebody's on the street there. Okay, so what did you get for your answer on that example? You pick the closest if you didn't quite get it. Is that random? Okay. All right. So, and I think I set up the problem a little weird. It should actually technically not be negative. That's already included, but I put them all negative, apparently. Okay. So one of you got it right, I guess. Negative 0.2079 per second would be the right. How many of you just randomly guessed? Is that everybody? Okay, so how did you feel about... So everybody guessed, and only one person got lucky. Kind of funny. So first of all, kudos to whoever that is, and you can, I guess, see the thing here. This, for me, today's... I'm not counting you off for wrong answers. I'm just having it as a participation activity. So congrats, whoever that is. All right. So what did you guys get hung up on for this problem? Just not have enough time, or didn't know where to go? What happened?
Well, I tried to solve it and I got an answer. I was like, I'm just going to get stuff from the data, but it doesn't work. And then I was like, wait, I didn't use KA for the pH. And I was just unsure of like how to manipulate them to use them for this.
Okay, that's good.
Why do we have the KA being 10 to the negative 7.54? Like, because I would have thought to just like do 10 to the negative 6 if I was like reading the problem, because the pH is given.
Okay, good questions. I will answer both of those in a moment. Anything else that's we're getting hung up on here? Just looking at the data part, did you know what to do with the data? No, so that was another hang up probably, right? So like, okay, we got data, what do I do with it, kind of thing? Okay. All right, that makes sense. And sorry for letting you bash your head up against that without better instruction first. Okay, so for the KA, there's good questions about what to do with the pH, what to do with this KA. I tried to kind of backtrack a little and say, okay, well, let's take the simple manner and say all of the HOCl is HOCl, and that is 1.8 milligrams per liter. So what I intended to tell you with that is none of this Ka stuff really matters if we assume that the wording of the problem says the chlorine, there's 1.8 milligrams per liter of HOCl. If we know that, even though it's giving us this temperature and this other stuff, we don't care because we already know the ratio. So I'll say if total chlorine, I'm just going to write total, chlorine equals 1.8 milligrams per liter, then we have a more challenging problem, okay? Because then we say, all right, we need to convert to a molar value of the total equals something, right? Then we say, okay, Ka, so Ka, and to answer the other question, Ka is the equilibrium constant for this particular equilibrium equation, right? So we have HOCl in equilibrium with OCl minus and H plus. And there's a Ka that dictates how that equilibrium goes, okay? And anytime we have an equilibrium equation like that, we say the equilibrium constant is equal to the products over the reactants, right? So in this case, we would say that would be H plus times OCl minus. So there's the products made in this reaction divided by the reactants, which would be simply HOCl dissociating. So with that, the 10 to the minus 6 comes in when we put in for H plus. Right? So the 10 to the minus 6 goes there. Okay, with that, we could say we could convert from this 1.8 milligrams per liter to a moles per liter of total, and then we can get a moles per liter of HOCl using the Ka equation. So we would then solve for HOCl equals some number. And actually what we could do, I'll write out how I would go about that, right? We would say this is going to be equal to, we multiply HOCl from both sides and divide Ka from both sides. So it'd be H plus times OCl minus divided by Ka. Now we have OCl minus, which is another unknown, right? So we actually need a system of equations here to get to our HOCl concentration. We also know that this total is going to be equal to HOCl plus OCl minus. So that lets us have a system of equations, because if this is X, we can then solve for OCl minus in terms of HOCl, and then substitute that in there, and then simplify. So then we would say, we could rewrite this to say OCl minus equals, I'm just going to write total instead of putting it as X. The total chlorine minus HOCl. And then we could substitute that into there and then solve for HOCl again to get HOCl by itself again. So more algebra, but it is all just algebra on that front. Okay, but none of that is dealing with the data yet. That's all complications if we have to solve the pH side of the problem, which I tried to simplify for you, telling you like, okay, let's just assume this wording is saying HOCl is all that. Because if HOCl is all that, then it becomes much simpler. We don't have to deal with any of this stuff. This is important, and my hope for you is that you learn to do so that you could do that in a problem like this and do all of these steps. But that is a bit elaborate, right? There's a lot to that. So going back to just the data, what we have here is time as the x-axis, and we have the number of pathogens here as a second column, number of plaque-forming units in this case. So that's going to give us essentially a plot of number versus time. Now, if you think back a moment, I sketched this out and I should have spent maybe a little more time on it. What I had just showed you was a plot of the log of n over n naught, and I mentioned that the natural log of n over n naught versus time, that slope gives us the k. Right, so I probably should have just drawn that up again for you for this problem, because that was really, my intent was for you to take the data and push it to this form so that you could process it, right? So what I was hoping for you to do is transform it to get the natural log of n over n naught as the y-axis versus time. And I guess I should rewrite that. Because if you do that, then you plot the data, then you can use a graphing calculator or Excel or whatever to get a line of best fit through that data, right? How many of you routinely use your graphing calculators for lines of best fit like that? Seeing some no's. How many of you are confident you could do that, like if I asked you to? No. Okay. This is really interesting to me because, like, I'm trying to remember when I stopped using the graphing calculator very often, but back when I was in high school and then in college, it was like we didn't. So I guess I had a laptop in college, but it was like a 17-inch monster. It just stayed in my dorm all the time, right? It was like if I had to bring it somewhere, it was like, okay, 10 pounds of laptop lugging around, right? So like I did everything on my graphing calculator. It was just like I knew it back and forth until like at some point in college, it's like I stopped using it so much, and then like my skills have deteriorated. The TI-83 broke at some point, and then I was like, 89, what's that? I don't know. And so I don't even know what's the latest graphing calculator these days, or even if you have to use it. But I say all that because I'm trying to adjust my expectations, and I think it would be worthwhile for you guys to be able to do so. Okay, how about if I told you to do it in Excel? Would you feel good? All right. Okay, so it may just be the graphing calculator thing, and I even feel a little bit of the same way, right? Okay. So if we do it in Excel, this is how I did it essentially. It's no longer relevant. Okay, so we had time, and I just put the data here, right? So I just copied it in here, and then I said, okay, well, one thing you could do is you could plot as the x-axis. You could be fancy and do c times t. Not doing that. Not planning to do that right now. Let's just do verse time. Then you could take the natural log of the starting concentration divided by the starting concentration. And the way I put that in Excel is I put a number sign on the second time I say that, so that when I fill it downwards, then it says, okay, now it's the natural log of the number at time 2 divided by still the number at time 0. Right, so that'll go down the list here, so on. And so we basically get the natural log of n over n naught. So then that's me linearizing the data. So then I can plot it, do the line of best fit, and it looks like this. So with time as the x-axis here, natural log there, the data is real data, so it's not a perfect straight line, but it's a good line. It's pretty clearly first order, even if there's some experimental error in the data collection, right? So then we can get a slope. Technically, we probably ought to fit that so that it's the intercept is 0. Would be better. See if I can. Because we know it has to run through 0. The natural log of n over n naught, by definition, is 0. The natural log of 1 is 0. So could do that even if the fit is slightly worse. That's a little more accurate, and we don't have to worry about the m. So that gives us a y value. Y equals negative 0.3758x. That value is going to be our k star. So we found then that k star equals 0.3857 or whatever it was. 3758. And that's per second. So with that, we can then go through this process, which is what I added there at the end, trying to kind of coach you through the last part of it, and not realizing at what point would you get to. So then that's k equals the k star over c. So we can solve for the k by saying, oh, we know this is 1.8 milligrams per liter. We have a value for k star now. That gives us a final answer in that manner. So let's see if I did that here. Okay, so we'll just say k then was equal to the 0.3758 divided by 1.8. Should have just done that. There we go. And that should be liters per milligram seconds. And hopefully that's the answer that I said was correct online. Yeah.
So the answer was negative 0.2 10.
Yeah.
But you said it wasn't supposed to be negative.
Yeah, we already know it's negative,
Yeah, I
so
didn't get a negative number, but so I kind of did it a different way. I didn't plot it,
okay.
but I took like R of n equals negative kc to the n power and then n to the 1. That equation.
Yeah.
And I took the derivative of both sides and just solved for k value.
Okay, but did you include the data in any manner?
I used the chart.
Okay, so use the chart and you so you said you took the last value of n.
Like, can you go to the PowerPoint?
Yeah.
So I took the time chart and
Yeah.
I did the initial n would be 6,152.
Yeah.
And then the final would be 300.
Okay.
And then the time would be 8 seconds.
So that was a great way to estimate it. So essentially you were saying, okay, I'm going to solve for n over n naught because I have values for those two, and I'm going to say n at time 8 seconds and set that equation to your rate equation. Yeah, that's an excellent way to do it. I wasn't even thinking about that when I said use your graphing calculators, because I was thinking line of best fit, but that also gives you a good estimate. Now, if the last data point was, looked a little different, like if we manipulate my data for a second and say that was a pretty underestimate there, the kinetics don't look as good, and your way of doing it would be much worse. But that's just for if the data was bad. If it's nice, good data, then that's a really good way to do it. Just a little comment. So congratulations for you to calculate it that way, even though it was like what I had in mind was this way.
Okay, so would my way be wrong?
Not necessarily. If you were doing that for an exam, let's say, I think that would be a great way to do it. For a research project, it would be technically wrong because you want to include all the data. So it's like if you were, that way you have an estimation based on the whole data set. So because your way is taking the first and last only into account. But a great effort and a great method for on the fly. Does that make sense to everybody? Kind of what happened? Okay, cool. All right, so this is kind of neat stuff. Another way you could think about doing it is just convert the x-axis into the CT. That's done pretty commonly. So if we did the CT here, then you can get, and again, we should put the this value through 0, set intercept. And if you did the CT and you said, okay, we're going to calculate that contact time and convert all of our x values here as 1.8 times the time, we can get a value here. We can get a slope that's giving us that k instead of the k star. And it should be the same. That negative 0.208 should have been the same here. So maybe, did I do something wrong? Yeah, I did. I wrote this in wrong. 3758. That's what happened. Okay, there we go. That's what, now they match. Good. Okay, so the Kahoot was more correct, and then we just talked about that was a better answer. Okay, so either way is fine. And just kind of wanted to show you, sometimes you'll see plots like this if you look at disinfection technologies, publications, things like that. You'll see contact time plotted against the survival fraction, or the natural log or even log survival fraction. Okay, I'm not going to plan to give you data on an exam like that, but if I were in your shoes, I would think to myself, oh, maybe I should jog my memory on how to do this in a graphing calculator. I don't even know where my graphing calculator is though, so I'm not too hard on you on that. I just think that I would be like, oh man, I feel like I should know this. Okay, I think I'll probably just let it off there, and we'll talk about UV disinfection next time. Any questions before you go? Okay, so we'll go through the exam next time, and then if that's quick, we'll start on disinfection or the UV disinfection, and if not, we'll just pick that up next week. Okay, I'll see you on Tuesday.